Good morning, everybody. Let me begin with thanking the organizers and all the people behind this institute for setting this up and for giving me the opportunity to participate. I like the place and the a lot. I'm going to tell you a story about the possibility of squaring the circle, or more precisely about relatives of this program that show up in the context of, or in some context of quantum information. In the end, this will be no-go results, as is the impossibility of squaring the circle. Let's start with this paradigm of a no-go result. So in fact, in Germany, there's this saying of, so there's this phrase of die Quadratur des Kreises, which basically everybody uses in order to say that something is impossible independent of how hard you try. And even if people on the street, they don't know exactly what the mathematical underlying problem is, they know this phrase, die Quadratur des Kreises. I know the quadrature of the circle. Okay, so let's remind ourselves what this is or was. So the task is to find a finite ruler and compass construction of a square that has the same area as a given circle. And this is maybe one of the longest open problems in mathematics, because it dates back, or at least this is what we know, at least to Anaxagoras around 500 BC. So he was, of course, a Greek philosopher who at some point in his life had a lot of time thinking about stuff because he was in prison, as it was common among Greek philosophers. And then I think he was in prison because of a lack of respect for the divine nature of the sun, because he claimed that the sun is just a big fireball. What an idea. Okay, he had time to think about this, but he did not solve it, and the problem remained open for more than 2,000 years. Right? And then in the end of the 19th century, Lindemann showed that it's not possible, which of course did not prevent people from publishing results that claim that it is possible. And one of the most famous, or infamous, is this a word? Infamous? Infamous? Along this line is by Edward Goodwin, who published in the American Mathematical Monthly, like 12 years after Lindemann showed that it's impossible, a paper with the title Quadrature of the Circle.
Published by the request of the author.
Exactly. So this published by the request of the author, which in my interpretation means that he paid. And back then, one could have learned that it's not a good idea to let the authors pay for a publication. We missed this opportunity. It's also this publication is also historically interesting because this was the basis of this notorious Indiana Pie Bill. Right? So this a couple of years later, or around the time, I don't know exactly the name, there was this effort by the state of Indiana to fix pi by law to 3.2. And this passed the House of Representatives. Well, I think at the beginning they said, okay, this is not our business, and then they moved this on to the Committee on Education, but then it came back with thumbs up, and then the House of Representatives said, okay, let's go for it. But then it did not pass the Senate because there was a mathematician around who politely pointed out that maybe this is not the best idea. Maybe not so politely. But back to Lindemann. So how did Lindemann show that squaring the circle is not possible? So first he paid attention in school, where he learned that there are different types of numbers. There are the rational numbers. And then there are those numbers that Pythagoras did not like so much. They are the irrational numbers. The algebraic numbers that are roots of polynomials with rational coefficients. And then in the middle of the 19th century, I think Liouville was the first one who proved that there's something outside this world, that there are transcendental numbers. And somehow I like the way Liouville observed this, because he studied how well algebraic numbers that are not rational can be approximated by rational numbers. And then he derived bounds for how well this can be done. So in terms of the degree of the polynomial and the size of the denominator of the rational approximation. And then he realized that he can write down numbers that are not rational, but can be better approximated by rational numbers than algebraic numbers, according to his bounds. Yeah, these numbers, they must then be transcendental. Okay, and so now back to Lindemann. Lindemann, of course, proved that pi is a transcendental number, and since everything you can construct a finite protocol with ruler and circle, you can describe in algebraic terms. So you can only get ratios that are algebraic and never anything transcendental. Right? So this was the way of disproving or proving the impossibility of squaring the circle. Proving transcendentality of a number is a subtle business. Yeah? So we know a couple of transcendental numbers, like e and pi and the natural logarithm of every integer larger than 1. But if you start to combine those numbers and ask, is e plus pi or e times pi or pi to the square root of 2, or these simple combinations, seemingly simple combinations, are these transcendental? We don't know. There are no tools around for proving this. In transcendental number theory, there's a big conjecture called Charnoy's conjecture. And if this would be true, then one could more or less easily prove that all these simple combinations are transcendental, but it's a conjecture. Okay. Okay, so this was about numbers. Now, there's, as you all know, there's a similar distinction between, let's say, algebraic on one side and transcendental on the other side, also for functions and for sets. So let me briefly go through this. So on the level of functions, we call a function algebraic if its graph is locally the solution of some polynomial equation. Right? And then, of course, there are the usual suspects of functions that are not algebraic, the exponential function and the logarithm. In the framework of sets, okay, there's also algebraic sets or algebraic varieties, but for the purpose of or in the context of quantum information theory, what is much more important is are semi-algebraic sets. Yeah, so what's a semi-algebraic set? It's a subset of some real vector space, Rd, which is described by a finite number, and the finiteness is crucial, of polynomial equalities and inequalities, like this torus. Okay. Yeah, on this side, so we saw an example already in Marco's talk. Yeah, so I'm very grateful that Marco somehow rolled out the way on which I'm now wondering. So we saw such a separation, and we saw an argument that I will use over and over again in the following examples. Okay, maybe let me go to a familiar example that makes clear why semi-algebraic sets are so ubiquitous in quantum information theory. Yeah, so first, we talk a lot about positivity. And the cone of positive semi-different matrices is a semi-algebraic set. Right? This is most easily seen by re-expressing positivity in terms of the minors, because we can just check positivity of the minors of the matrix, yeah, and then these are polynomial inequalities. which then shows that the positive semi-definite cone is semi-algebraic. But then there are a couple of nice closure properties of the sets of semi-algebraic sets that basically tell us that we can do a lot of things with those sets without leaving the semi-algebraic world. And the basic theorem behind this is this Tarski-Seidenberg theorem, which tells us that if we start with some, let me do an example. So let's write down the set of quantum channels, and I'm staying in finite dimensions throughout. So let's say I consider linear maps from MD to, for simplicity, I keep the dimension the same. Yeah, maybe let me put a little h here for denoting that I only consider Hermitian matrices. So now, how can we characterize quantum channels? So first we need to formalize complete positivity. And one way of doing this is to say, well, no. I'm sorry. Let me first write and then talk, because I cannot do both. Complicated way of writing things now. So what we do is we extend the system, so we tensorize with another system, and then we check positivity, right, by plugging in some positive operator and taking the trace with another positive operator, and this has to be positive, right? And this is complete positivity. Now coming back to Tarski and Seidenberg. So what this theorem basically guarantees is that if we start with some semi-algebraic, or let's say we start with something that is characterized in terms of algebraic inequalities and equalities, and then we throw in quantifiers like this one and that one. As long as we quantify only over sets that are themselves semi-algebraic, and this is semi-algebraic, then the entire sets will remain semi-algebraic. And more precisely, Tarski and Seidenberg, they guarantee that one can eliminate, so in principle, one can eliminate those quantifiers and write down an equivalent quantifier-free expression, quantifier-free formula. Okay. But now there's a potential troublemaker around, and this is this guy here. Of course, for this case, we know that we can bound this, right? So this is not really a quantifier over all integers. But in general, something like this, so quantification of the integers, this is the nemesis in the semi-algebraic world, right? Because this is what can potentially kick you out of this world. And as long as something like this is not around, okay, I should not cross this out, right? But I just can bound this by a dimension squared, or by the dimension. This theorem by Tarski and Seidenberg is the cheapest way of showing that something is decidable. Yeah, so that membership problems like also the separability problems, or where we want to decide whether a given bipartite density matrix is entangled or not. We can write this down in a similar way with some quantifiers, and a priori it might be difficult to come up with an algorithm, but Tarski-Seidenberg tells you there's an algorithm, it's just not efficient, right? Because the runtime is typically doubly exponential in the number of variables, so you probably don't want to use it. But there exists one, so it's a decidable problem. So occasionally one has to be a little bit careful, I think, with the field over which one is working eventually, right? Because one needs to work with a computably ordered computable field. So it's not sufficient to only work with computable numbers, because the field of computable number is not computably ordered, and then this could cause a problem. If one takes a field of algebraic numbers, for instance, then everything is fine. Okay. You should ask questions if you have.
Stupid question. So you wanted all the quantifiers to be for all here, right? You wanted here to have the complete qualitative maps? Because you said that you wrote only exists A.
No,
You wanted all of them to be for all, right?
I'm completely stupid.
Okay.
This is all, there's no. Thank you.
What about the complex numbers?
Sorry?
The complex numbers?
There are no complex numbers. There are no complex. So in the end, this is. It's a real vector space.
Okay, but the real numbers are fine too.
And so this. Okay. So in the complex case, there's also so there's an analog of the Tarski-Seidenberg of this quantifier elimination theorem. And so over algebraically closed field, it's Chevalet's theorem, I think, which is a little bit easier and a little bit stronger, also in the sense that so you start with stronger or weaker, depends on the angle, with so this deals with constructible sets. Yeah, so you don't have inequalities then anymore, because you're working over the complex numbers, but you deal with polynomial equalities, and then you have those quantifiers, and then Chevalet's theorem tells you, okay, you can eliminate all of them, and then you end up with a finite number of polynomial equalities or inequalities without quantifiers. But for most of the applications I have in mind, the spaces are essentially real, right? Even if complex numbers show up, but they do not show up in the sense that the vector spaces are real, because we deal with vector spaces for which. So this separation between algebraic or semi-algebraic on one side and transcendental on the other side, this often comes hand in hand with another separation, namely between single shot theory or finite theory on one side, and asymptotic theory or the thermodynamic limit on the other side. Let me give you an example which goes back to the paper that Marco quoted already. So this 92 paper by Farnes, Nachtigall and Werner. So there they pointed out the following. So if you consider a system of n spin 1/2 particles, we have n qubits, and imagine that these sit on a ring, and neighboring pairs, they interact. They interact according to the antiferromagnetic Heisenberg model. Yeah, so this is the physicist's way of writing Pauli x tensor Pauli x plus Pauli y tensor Pauli y plus Pauli z tensor Pauli z. Okay. So you have this Hamiltonian translation invariant on a ring, and then you can ask what's the ground state energy. This ground state energy, since the Hamiltonian is algebraic, and then you minimize this by either invoking Tarski-Seidenberg or the closely related Tarski transfer principle, you can argue that whatever the ground state energy is, it must be an algebraic number. Right, because you have something that is purely algebraic. There's no way you can get something transcendental out of this. If this ring is finite, right? But then if you take the limits of n, the number of particles going to infinite, the thermodynamic limits, then you end up with some number where the logarithm of 2 appears, and this is a transcendental number. And Farnes, Nachtigall, and Werner used this fact for the following separation. This is rephrasing a little bit what they do. So if you consider the set of all 2-qubit density operators, then so it's a convex set. Then inside this convex set, you have a convex set of all 2-qubit density operators that are reduced states of a translational invariant state. So translational invariant on the infinite chain. Okay, and this is a easy to formulate, but otherwise weird constraint. And this set is not known, not explicitly. Right? You can define it, then it's kind of implicitly known, but there's no explicit expression for this set. But there's, and this is what Farnes, Nachtigall, and Werner basically did, there's a hierarchy of approximation from within the set. This is given by these C-star finitely correlated states that Mark was talking about. And so these data are also called matrix product states. But the construction of these C-star finitely correlated state or matrix product state, this is purely algebraic. So this also means that whatever energy you get using those states as an ansatz state for the Heisenberg model, it will always be algebraic. And this is true for every level in this hierarchy. And then they argued that that the ground state of the Heisenberg model, since the ground state energy is transcendental, cannot be a C-star finitely correlated state, or not be a matrix product state with finite bond dimension. Okay. Yeah, and there you see this. I was trying to say that that the separation between algebraic and transcendental often comes hand in hand with the separation of something being finite and something being infinite, in this case the thermodynamic. And you used the same kind of reasoning. Right? Okay, so now let me, what I'm doing. So now let me tell you something entirely different, and in order to come back at some points to this separation. So now I want to talk about catalytic state transformations, just to motivate a little bit of what I'm doing on the next slide. Okay, so what are catalytic state transformations? So this is an idea Henrik Wilming worked a lot on. And the task is the following. So you're given a density operator, rho, and as often, what you have is not what you want. You want something else. Okay, and then the question is, how can I get there? But there are rules of the game. The rules of the game are, starting with rho, you can borrow another density operator, sigma. So this is the catalyst in the end. And then you're allowed to do a global unitary on both of them. And the constraint is that on this additional ancillar space, you want to recover sigma, this catalyst again, because otherwise it would not be meaningful to or reasonable to call this a catalyst. And you want to get this exactly. Yeah. No embezzlement. No.
Understand the model.
Is this a question? Yes. Exactly. And then, so under this, within this framework, under those constraints, the question is, what kind of reduced states rho prime can you obtain? Yeah, what is reachable? Okay, so let's. Now let's define two sets. So first I want to define a set Cn, which is basically the set of all states that are reachable within such a framework, if at least to arbitrary good approximation, if we constrain the catalyst to one that lives in an or acts on an n-dimensional Hilbert space. And okay, for some, I would say, technical reason, I throw in these approximations, but you can just ignore maybe those approximations. Yeah, so this is the set of states, the set of rho primes that you can reach using an n-dimensional catalyst to arbitrary good approximation. Yeah.
So you have rho that you can change, no? That's, so
no,
the set of output state you can reach.
Exactly. So I fix rho. Yeah. So this is the state that I have.
Rho is fixed.
Rho is fixed. Exactly. Yeah. And then I want to know. So starting from rho, what can I reach?
So your freedom is the unitary.
My freedom is the unitary and the ancilla. Yeah. But what are
too.
exactly, and the catalyst. Yeah.
And n is free as well. The number n.
Okay. So n for now is this the constraint. Yeah. So for every n, I get a set, and of course these sets they will include each other. So this will be an onion type structure, right? Okay. Now, before I come back to the set, let's define another set, namely the set of density operators rho prime that have larger entropy, von Neumann entropy, than the initial state rho. Okay, so why is this an interesting set in this context? Well, because subadditivity of the von Neumann entropy demands that whatever rho prime I get, this is fulfilled. Right. So why? Because we start with this product state, then we act unitarily on it. So the unitary globally does not change the von Neumann entropy. Right? And then subadditivity tells us that the sum of the entropies of the reduced states is at least as large as, well, the sum of the entropy of the initial states. But one of the reduced states is the same as before. Yeah, so this means that the entropy of rho prime has to be at least as large as the entropy of rho. So this is necessary. And the remarkable result of Wilming is that in the limit, it's also sufficient. Yeah, so if you take the entire onion, so now if you relax this constraint on the dimension of the catalyst, then these sets coincide up to closure. And then there's immediately the question popping up, well, do we need this limit? Yeah, or is maybe a finite ancillar dimension sufficient? Maybe a dimension that depends on D, but as it was here. Right? So here we can restrict to n equal to D. So the answer is no. And the way to see this is very simple. I would say it's almost obviously no. Right? Why? Well, because of the following color coding. Right? So here we see something semi-algebraic. We have these polynomial equalities and inequalities with some quantifiers. Okay, but then Tarski-Seidenberg guarantees that, well, this is a semi-algebraic set. This set does not smell very semi-algebraic because there's a logarithm involved. So if this would be transcendental, then this would mean, well, there cannot be a finite dimension, such that it's sufficient to choose the catalyst from this finite dimensional space in general. Okay. So are these entropy constrained sets transcendental? Well, the smell transcendental? Well, it depends on the dimension. For dimension 2, they are obviously not. Right, because in dimension 2, if you look at the set of density operators with a given entropy, or with entropy larger than a given number or smaller than a given number, it doesn't matter, then we know that these are very these are very algebraic, yeah, and therefore also semi-algebraic, because we can equivalently characterize this set in terms of the purity, for instance. Right? It's just a sphere, and a sphere is very algebraic. Yeah, and the mere fact that there's a logarithm popping up in the definition does not mean anything. At least not for dimension 2. For dimension 3 and larger, it does, and all those sets, they are nowhere semi-algebraic. Okay, and let me show you one way of proving this, which might also be useful in other contexts where one wants to prove that something is not semi-algebraic. Okay. And it's a proof by contradiction, so we assume that the set is semi-algebraic. Let's say this blue set is the set that we consider. Yeah, so this is a set of density operators with, let's say, constant entropy. Then what I do is, since this is implicitly defined, which is a little bit hard, I look at something that I can write down more explicitly. Yeah, and therefore I take, for every state rho in the set, or on the boundary, I consider a normal vector, a unit normal vector. So which essentially means that I apply the Gauss map, which maps every point to a unit vector. And then I exploit that if this set is semi-algebraic, then also the normal bundle will be semi-algebraic. Okay, and then I look at a small path that goes through the points I'm considering, and this path is supposed to be constructed in a way that it comes from an intersection of something algebraic with the considered set. So if the considered set would be semi-algebraic, then this path itself would be semi-algebraic. Okay. Then after applying the Gauss map, we also get a path on this unit sphere, and this would still be semi-algebraic. Okay, and now I'm considering just one coordinate of this path, right? And then I get a function from R to R, so where the initial R is the parameter of this path, and the final R is just the coordinate of the map of the image of this path. And this map from R to R I put into the complex plane, and then I say analytic continuation. Okay, and then one can exploit something that we have learned in our complex analysis class, namely that algebraic functions, well, they may have several branches, but they only ever have finitely many of them. Yeah, or in more technical terms, the Riemann surface is compact. Right? But if we do this for this particular example, where this is the set of density operators with constant entropy, then what we obtain is a non-compact Riemann surface. So we get infinitely many branches, which of course come from the infinitely many branches of the logarithm. And this can be done at every point. Yeah, so for every neighborhood, one can show that this set cannot be semi-algebraic.
Where did you use the extra dimension here?
So because yes,
what
exactly.
that cannot work.
Yeah, because for dimension 2, there are too many constraints, and in the end, there's nothing left. I want to have basically a curve left. If there's only a point left, then there's nothing to be done. So a little bit more formally, so for dimension larger than equal to 3 and C strictly in between 0 and log D. Of course, the value of the entropy must not be extremal. Because if it's 0, the set is semi-algebraic. If it's maximal, the set is also semi-algebraic because it's on a single point. But for every value in between, the set is nowhere semi-algebraic, which means that for every point in the set we pick, and every neighborhood intersected with this set is a non-semi-algebraic set. All right, which, coming back to this these catalytic state transformations also means that there's no algebraic single shot characterization of the entropy function unless it involves an infinite ancilla. Now one can extend this idea and, for instance, throw in additional constraints. Yeah. So let's say we do not only want to constrain the entropy, we also want to constrain something else, like the energy or the distance to some given set. And suppose that this additional constraint is given by a differentiable function, by a C1 function, which I think this is too strong. This. Yeah, I think this need not be from the entire matrices, but just from the Hermitian matrices, and they're only locally into the reals. So now, if we consider the set of density operators, let me use my hands with fixed entropy and this additional fixed constraint, then under additional technical assumption, which I will talk about in a second, one can still show that the set is nowhere semi-algebraic unless it's empty. Yeah, so unless of course the constraints are such that there's nothing left. Okay, and there's an additional assumption that one needs, and the simplest way of imposing this additional assumption that I found is to impose that in the neighborhood that we consider, there's at least one point where the gradient of this additional constraint function does not commute with a point. Yeah, so this is kind of a first order way of saying that the additional constraints must not only involve the eigenvalues. Yeah, so it must also involve the eigenvectors. Because if it would be allowed to only involve the eigenvalues, then what we could do is, for instance, we could fix an eigenvalue to a constant, and this would reduce effectively, for instance, the three-dimensional case to the two-dimensional case, where we know that the result cannot hold. Okay, but as long as this additional constraint also, in some sense, in this sense, for instance, involves the eigenvectors, this cannot happen. Okay, and now one can extend this to other similar quantities. So, for instance, one can show that the relative entropy, so the standard von Neumann relative entropy, if we consider this with one argument fixed, or with the other argument fixed, or as a function of both arguments, all the level sets, they are nowhere semi-algebraic. And similar holds for the mutual information, right, which is in the end just a relative entropy. Which also means that, as in the case of the entropy, also for those quantities, there cannot be any algebraic single shot characterization unless some infinite ancilla is showing up.
So if you have an infinite ancillas, then it is semi-algebraic. Then you know it's semi-algebraic, or?
No. So if there's no infinite ancilla, then, well, if you start with something with an algebraic or semi-algebraic expression, then you end up with something semi-algebraic, right?
Yeah, but
then you cannot describe these level sets.
But now, if you have a description at the limit with an infinite dimension.
But as this example, of catalytic state transformation shows, if you allow to go to the limit, then you can describe these sets in an algebraic way. Right, but the set is not semi-algebraic. You have basically, speaking in terms of Tarski-Seidenberg, you have this quantifier. You have some quantifier over the integers, right, which kicks you out, or which potentially kicks you out of the.
It's an infinite intersection of semi-algebra.
Exactly, and then you don't know what happens.
Well, I mean, your result
I was
told you
wondering
that
about your ancilla comment.
you said that there is an identity that Wilming proved that.
Yes, exactly. Yes.
The question was about this ancilla comment. Maybe I still don't understand. The ancilla, you say unless the ancilla is definite dimensional. Is that something wrong there?
Yes.
Yeah.
So let's take this Wilming framework of catalytic state transformations. Right? So there, if you allow for an infinite dimensional ancilla, then you can describe these entropy constraint sets basically in a single shot way with this algebraic. But nevertheless, the set is not semi-algebraic. Think about this coming from this
The
limit.
question is for mutual information, what is the analog of that Wilming thingy?
This I don't know. This is I don't know whether this is known.
But it would be super nice.
Yes, of course. Yes.
You know something about decidability of membership in this set?
Decidability of whether or not the entropy is smaller than or larger than a given number.
I mean this in this catalytic thing. So all these rho primes that you can get from rho. No. Okay. It's you have
It's just the entropy that decides. As long as you can compute the entropy, you can decide. Yeah. I mean the tricky question, I think this is not known, is how large does your ancilla have to be? Yeah? So you cannot have an a priori bound on the dimension of this ancilla, but of course in many cases a finite dimensional system will be okay. And then the question, how large does this catalyst have to be? I think this is not known. Okay.
I think there is one question which is not clear. If you are given state, of course, for a certain degree of approximation, a certain number n will work. Whether that relation between state, epsilon, and n is a good computable function in a way, right? That remains. Probably there's some suspicion that this is a bad function. Given rho and epsilon, how large is the n?
Exactly.
Which does it up to epsilon?
There's nothing. At least I know nothing about this.
Maybe we'll say something. But what about d equal 2 and the original question?
Okay. Good question. So, as you realized, the argument doesn't work for d equal to 2. I don't know. My guess would be it's still true, right? It's still true that you cannot bound the dimension of the ancilla. And if you look at the protocols that Wilming and co-authors found, then you see that also there you need infinite dimensions. But I think strictly speaking, or at least I don't know a proof, but I haven't really tried to close this gap. Good. Are you ready for a new story? New chapter? Okay, reset. I want to talk about something similar to what Marius talked about, complexity. And I want to start with a classical case and first look at Boolean functions. And there's because the situation is for me is shocking. Right? So in 49, Claude Shannon made the following simple observation. If you look at all Boolean functions defined on a bit string of length n, you map this into a single bit, then we know that each of those functions can be represented by a circuit that uses only AND, OR, and NOT gates. And then you can assign a complexity to every function by just asking what's the smallest circuit that represents this function. And then you can do a counting argument. It's a very simple one, and Shannon, I guess, was the first one who did this. And realize that almost all Boolean functions have exponential complexity, because there are just so many Boolean functions. Right? You have a domain of size 2 to the n, right? And from that you map into 0 and 1, so you have 2 to the 2 to the n Boolean functions, right? And then if you come with polynomial size circuits, it's just not enough. Yeah. And you can refine this counting argument a little bit and then formalize the statement that that almost every Boolean function has exponential complexity. Okay. Despite the fact that we know this and that the argument is super simple, there's no explicit example. And it's even more shocking, we don't know any explicit example. Okay, an example is always a family of examples, right? Because you want a family where you have an element for every n, because you want to talk about the scaling in n. So we don't know any example where there's a 4n, so linear lower bound. The best explicit example where there's a proven lower bound on the circuit complexity is 3n plus something. Yeah, so if you prove 4n, then you achieved something. Right? Then it's state of the art. Okay, so this is the classical picture. Okay, now let's go quantum. Now in the quantum case, what's the complexity? So I use a different notion than Marius used. I used the standard circuit complexity applied to both unitaries and states. So let me start with unitaries. Yeah, let's say so we define the complexity. The complexity. So speaking, it's the circuit complexity of a unitary U that acts on, let me take qubits. I have n of them is similar to the classical case that I was talking about. It's just the minimum number of 2-qubit unitaries that you can compose in order to build up the given unitary U. Yeah? So where each UI, let's say up to a permutation of tensor factors, depends on I, is of the form the 2-qubit unitary tensor the identity on the other n minus 2 qubits. So this is the circuit complexity of a unitary. And there's also the notion of circuit complexity of a state. So maybe let me plot this down for pure states. And this is, at least concerning the definition, this is closely related. So if you have a state, a pure state, psi, then you define its circuit complexity as the minimum circuit complexity of any unitary under the condition that psi is equal to the unitary acting on a product state. So in the end, you count the number of gates that you need in order to produce the given pure state psi starting from a product. Okay, and now the picture in the classical case is basically the same as so the picture in the quantum case is basically the same as in the classical case. So pictorially, well, the way to visualize this is of course in terms of these circuit pictures, right? Where every line is a qubit, and there are these gates, and then you minimize overall circuits that represent the given unitary or that produce the given state, and the smallest number of those gates is the complexity. Okay, and one can show that that the complexity is always bounded, say, of a unitary and also of a state by up to a constant, which I don't know. That's 2 to the 2n, and it was realized very early and can be found already in the book by Nielsen and Schwang. That's well for almost all unitaries and also for almost all states, the complexity is essentially 2 to the 2n, or is exponential. Yeah, so the picture is similar as in the classical case. And what is also similar is that it's pretty hard to prove even linear lower bounds for quantum states or quantum unitaries. And so there are topological states for which linear lower bounds have been proven, but otherwise I do not know of many results.
Linear means just linear and n.
Linear and n, yes.
So not exhibiting the square root of the dimension, but the logarithm, right?
Yes, exactly. So now what I want to do is sorry, too fast or too slow, depending which part of my body. What I want to do is I want to construct an explicit example with exponential circuit complexity, and I want to do this using this algebraic transcendental mindset. So what I will need is the transcendence degree. And before Miguel asks why do I want to do this, why not? If somebody tells me that the world is full of unicorns, then I want to see at least one. Right? So let's. So I need basically two notions. I need a notion of algebraic independence and of related notion of the transcendence degree. Yeah, so let's say we have a couple of numbers. Set a1 up to an. So these are complex numbers. So this set is called algebraic independent. I give for every polynomial in n variables over the field of algebraic numbers. If we insert the numbers from our set, and we get 0, then p has to be 0. So there's no algebraic relation between those numbers, and if this is the case, we call them algebraic independent. And then
You're allowed to ignore that. That is the fire test.
How long does it go?
I don't remember.
am I already running overtime?
That's
4
awesome.
minutes. Oh my God. Okay. That's a pity. So then the transcendence degree of a set is set C in the complex numbers is the largest number of algebraically independent elements in this set. And this transcendence degree has nice properties. In particular, so if you think about the list of axioms that Marius gave for complexity measures, there was this sub-additivity property, and this is exactly something that the transcendence degree has. Yeah, so if you take two tensors, then you can assign, if you regard these tensors just as a bunch of numbers, an array of numbers, then this tensor has some transcendence degree. You take two of them, and then you either glue them, or you contract them, or you take the sum, you do anything algebraic with them, you get a new tensor, but this new tensor has transcendence degree that is bounded by the sum of the transcendence degree of the initial tensors. Right. And this immediately gives a lower bound of the complexity in terms of transcendence degree. So then it's basically trivial that the circuit complexity is lower bounded by 1/16, because there are 16 entries in at most 16 entries in every gate, times the transcendence degree. So if you want to construct an explicit example of exponential circuit complexity, then this is now reduced to constructing something that has exponential transcendence degree. And this can be done. Right? And this is, I'm sorry, I thought I was much faster than I am. Okay, so you can start with the first n primes and then multiply them in a little bit in some way, and exponentiate these numbers and build up unitaries or states from there. And then there are two results that one can use. An old result by Bezikovic that says that this set of algebraic numbers is a large set, so an exponentially large set of numbers that are linearly independent over Q. And then one can use the Linnemann-Weierstrass theorem to lift algebraic to transcendental and linear independence to algebraic independence. So using these two ingredients, one can prove that these families that every element in this family of unitaries or states has exponential complexity. Okay, and then in the end, skip this. There's also something that one can say about hardness of approximation, because this was about the exact circuit complexity. You can ask, well, what about if you allow for some errors, right? And then one can show that if you look again at this family where every element has exponential exact circuit complexity, then one can show that every, let's say, all but a double exponentially small fraction of elements in this family still have exponential complexity if you allow for constant error approximation. And constant error means error 1. Yeah, so we look for an approximation in the ball with radius 1 in Hilbert space, which is a huge ball. Okay. Now this, however, this is not explicit. I mean, this is only we can only show this for the entire family in the limit. Similar for the unitaries. And the reason why I'm skeptic that we can achieve more with this is a result by Aronson, who showed that if one would pinpoint a single example where one can show that also approximation is hard, then one could separate BQP from p to the sharp p. Right? Okay, and since BQP contains p and p to the sharp p is contained in p space, right, this would separate polynomial time from polynomial space, which would arguably be the biggest result in complexity theory ever. Yeah, which makes me a little bit skeptic that one can improve this result. However, this is only true if one shows if one pinpoints an explicit state. For unitaries, such a result, such an implication from complexity theory is not known. And the unitary case is a little bit different. Also because in the case of states, complexity is very basis dependent. Because if I change the basis, then I can make the state a product state, right? Or I can come from a product state and change the basis and get exponential complexity. In the case of unitaries, this is not true. So the construction I gave you is completely stable with respect to all unitaries, because the complexity is purely in the spectrum of the unitary. Yeah, so I can mess up all the eigenvectors and still have exponential complexity. Yeah, so there's a difference between unitaries and states, and maybe this means that in the case of unitaries one can do more. Okay. Yeah, I think I stop with thanking or mentioning and thanking the people who did the work. Yeah, so there's Josa Blockhay, who did the work on transcendental properties of entropy constraint sets, and Yi Fan Yia, who worked on these explicit examples of exponential circle complexity. Thanks.